In this video, we're going to start talking about a Taylor series, and I'm going to explain kind of as we go what that is, and we're going to kind of culminate with seeing what the importance of it really is. We're going to start with a tangent line, okay? We're going to find the line tangent to the curve at natural log of x and x equals 1. So a tangent line, remember, just needs the two things. It needs a point. So we know that x is 1, the natural log of 1 is 0. So there's the point. And the slope, well, we need the derivative of natural log, which is 1 over x, evaluated at x equals 1. So the slope is also 1. So my tangent line is 1, x minus the x-coordinate plus the y-coordinate. Now, that's how I usually write it, and that looks great. I'm going to just change this a little bit, and you'll see why in a second, to be in this order. Okay? Now, my question is, at the point of tangency, what things are the same? So let me bring this graph in. Here it is. This is, the red, of course, is natural log, and the blue is the tangent line. So the question is, what two things are the same? Well, they meet at the same point. They meet at the same point. They both touch at the point 1, 0. So both f of 1 is 0, and, and they also have the same slope at that point. Okay, so those are the two things that at the point of tangency are the same. They meet at the same point, and they have the same slope. And of course, we talked about linearization earlier this year and last year, and talked about the fact that for points right around the point of tangency, the line and the curve are very similar to one another. Okay? At the point of tangency, they're exactly the same. For points around the point of tangency, they're approximately the same, or close to the same. Let's go a little further. So the question is, if we can make both the first, we made the function kind of match the derivative match the function, why couldn't we do that with the second derivative? So instead of just saying they have the same slope, we could try and make them have the same concavity. So instead of a line, I'm thinking of a parabola. Okay, so think about this, instead of a plus b times x minus 1, I'm adding this additional term. I'm saying we're also going to go a little further and try and have a curve fit in there and think about concavity and fitting a curve within. So the function, the function's value was, or the function was f of x, natural log of x. So f prime would be 1 over x, or if it helps you, it'd be x to the negative first. So the second derivative would be negative x to the negative second, or negative 1 over x squared. So I'm going to fill this in. F of 1, we said, was 0. F prime of 1, well, if I plug 1 into the derivative, I get 1. F double prime of 1 is negative 1. So what I'm going to try and do is I'm going to make a polynomial, right? Before it was just a line. I was just having a line that had the same, really would have the same term here and the same slope. But now I'm going to try and go one further. So if I think of the function, f of 1 should give me 0. But then if I plug 1 into the polynomial, I should also get 0 because I'm trying to make them match. Okay, I'm trying to make the polynomial the same as the function. So let's think about that. Okay, if I plug in 1 to the polynomial, well, of course, these two terms are 0. So it turns out that a is simply 0, this first term. Okay, now let's go a little further. I said that f prime of 1 should be 1. Well, let's find the derivative. Okay, so this is y, so let's think about what y prime would be. Well, the a is a constant, so the derivative of a constant is 0. Derivative of b times x minus 1 is just b, and then I have 2c times x minus 1. Okay, so if I plug 1 into the derivative, I get b plus 2c times 1 minus 1. This is gone, so that means that b must be 1. Now I want you to notice right now that what I've just found, if I put 1 right here, is the tangent line. You know, that was the tangent line I found in the previous slide. Now I'm going to go one further, the second derivative. Now the second derivative, if I bring it down here, the second derivative, remember that b is a constant, so it would be gone, so the derivative would just be 2c. So I should have negative 1, right? The second derivative, according to what I found, the second derivative needs to be negative 1, and that needs to be equal to 2c. So if negative 1 is equal to 2c, then of course c is equal to negative 1/2. So I could put that up here. So my polynomial is y equals 0 plus 1 times x minus 1, that's the tangent line, minus 1/2 x minus 1. Now again, the reason I was able to construct this is I wanted the function to have the same value as the polynomial. I wanted the derivative of the function to have the same value as the derivative of the polynomial. I wanted the second derivative of the function to have the same value as the second derivative of the polynomial. So I found my derivatives, found the derivatives of the polynomial, and simply set them equal to each other. And the idea is if they have the same value and slope and now concavity, I'll have an even better fit than I used to. And you can see that's true. I have the graph in red of natural log. I have the graph in green of this new parabola, and you can see I still have this point of tangency right here, but it fits for a longer period of time than the line, which just cut through like this. It fits for a little bit longer. So now the question becomes, could you go even further? Well, let's try. So now I'm going to try and make not only the first and second derivative, but also the third derivative match. So again, you want the function and the polynomial to have the same values at all of these derivatives. So natural log, okay, its derivative was 1 over x. Its derivative was negative 1 over x squared, or if it helps you, x to the negative second, negative x to the negative second, and its derivative would be positive 2 over x cubed. This is the third derivative, okay? There we go, third derivative. So the third derivative's value at 1 is 2. Well, I want the third derivative here to be the same thing. Okay, so the derivative, of course, of a is nothing. The derivative of bx is b. Then we've got 2c, x minus 1. Then we've got 3d times x minus 1 squared. Second derivative would be 2c plus 6d times x minus 1. And the third derivative would be b, or 6d. Okay, so we want this to be equal to 2. So that means that d is 1/3. So I mean, we knew from the previous slide, we knew that this was 0, this was 1, this was negative 1/2, and now we know that this is 1/3. So my polynomial becomes 0 plus 1 times x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed. So now they're going to have the same value, slope, concavity, and third derivative. Look at this. Look how good it begins to fit in here. Okay? Now, what if I went to the fourth derivative? Well, the fourth derivative would be negative of the function would be negative 6 over x to the fourth. So its value at 1 would be negative 6. The fourth derivative of the polynomial, well, what we'd have to do, of course, is we would add a term. right? And you can see I did that here. I added this term at the end. So these terms would all be gone. The first time, I'm going to kind of just do this. The first derivative, I can write first derivative just like that would have been 4e x minus 1 cubed. The second derivative would have been 12e times x minus 1 squared. The third derivative would be 24e times x minus 1. And the fourth derivative would be 24e. We want that to be equal to negative 6 because remember, we want the derivative of the function and the derivative of the polynomial to be the same. So e is going to be negative 1/4. So now, in the interest of space, I'm going to go back up here, and I'm just going to add that term at the end. So I've got minus 1/4 of x minus 1 to the 4th. Okay? Let me pull that out so you can see how it's matching now. Okay? So you see it's a 4th power, and then it matches for quite some time. Let's do one more. So in the interest of time, I've listed the derivatives of the polynomial and function as well as what we had so far for our polynomial. So the fifth derivative, see right here, 24 over x to the fifth. So evaluated at 1, fifth derivative's value is 24. Now below that, here was the original function, and I'm going out, I'm trying to make a 5th power. So I'm trying to make not only the original value, but the derivative, the second derivative, third, I'm trying to make them all equal to each other. So I've listed them out. Here's the first derivative, second derivative, third, fourth. Now we've already made those 4 or 5, kind of the original function, equal. So now I'm trying to make the 5th derivative equal. Okay, and it, of course, needs to be equal to 24. So divide both sides by 120, reduces to 1/5. And you might have kind of expected that, being as the pattern is what it is. So we got 1/5 x minus 1 to the 4th power. So in general, if you were thinking about this as a general term, you'd say, well, it alternates, right? First term's positive. We could really even kind of forget about that x equals 0. You'd say, well, I always have a 1 on top and an n on the bottom. And I always have an x minus 1 raised to the nth power. Okay, kind of take a look at that. We've got a squared and a 1 over 2, cubed 1 over 3, fourth 1 over 4, and that should be a 5th power right here, like that. So this is my general term. Now let me just pull out what this looks like again. So here it is. The original is in red, and the 5th degree polynomial is in the dotted blue. Now, on the next slide, I'm going to show you the generation of these one by one. Line, parabola, cubic, 4th power, and the 5th power. So you can see as we add more terms, it becomes a better and better fit of the natural log.